This is what happens when a population goes through exponential growth. The rate at which this curve bends upward depends on Rmax. Okay, if Rmax is very high, after only a few generations, that population is growing extremely rapidly. It might be doubling every generation. When you get into lower values of Rmax, the growth is much slower. So here, for example, R might be 0.01 or something of that nature, but you'll notice that even this curve is still bending upwards. And if you give it enough time, it will also be climbing as fast as this curve is, because it always keeps bending upwards. It never stops bending upwards, it never starts bending back downwards. And so forever on into the future, as long as this really describes how a population is growing, the population just grows faster and faster and faster. Is this biologically meaningful? Is it relevant? Well, yeah, in some cases it is. Here's a graph of the number of seals on the Santo Año Islands. This is Marunga angustura rostis, the elephant seal that was hunted almost to extinction off the California coast. There are an incredibly small number of individuals that survived, but once they were protected, they made this astonishing comeback. The line that's shown here is what happens if a population is really growing exponentially. You can see, whoops, sorry. You can see that it's in fact a very good fit for the actual data. Once these seals were protected, their population did grow according to the exponential model. Okay, this brings us to our second thing that you can do with a model. We've taken the basic fundamental facts of organisms. They are born and they die, and you put those together into a mathematical model, and the simplest possible model you get is the exponential model. Now let's do something that might actually be useful with this, and let's take it out in the real world and try to use that model to make predictions. Okay, this is the area of the world in which we're going to make those predictions. Specifically, we're going to look down here. Sorry about the bad quality of this graphic. This island is the island of Tasmania. It looks like this. It's reasonably chilly because you're fairly close to the Antarctic here. So it's a temperate climate, these rolling hills, and in places where there aren't trees, there are a lot of pasture. And the Europeans, specifically the British, who came to that area early in the 1800s, thought that it was a wonderful place to ranch sheep. This is sheep. In the year 1810, the first sheep were brought to the island of Tasmania, and there were about 25 of them in 1810. If you were hanging around on Tasmania between 1810 and 1820, you would have seen the population rise up to about 100 individuals. If you've been watching and doing some math during that time, you would have calculated that for every sheep that died on Tasmania, 1.175 lambs were born. Okay, so for about every 1.175 lambs born, there was one sheep that bought its last baa. So that's the births per capita minus the deaths per capita would be 1.175 minus 1. It gives you a value for R of 0.175. And that's the per capita rate of increase for sheep on Tasmania when they're getting plenty of everything that a sheep needs. Okay, this is a model of exponential growth, and if you use it to predict what the population size of sheep in Tasmania will do over, say, the next decade, it actually does reasonably well. This is the sort of thing you want to be able to have. This is the sort of model you want to be able to have if you say you are interested in predicting the mutton market in the area. We use our model. It says, well, if the intrinsic growth rate, if the per capita growth rate of the population is 0.175, and you've got 100 sheep in the year 1820, well then by the year 1830 you ought to have about 500. And it turns out the model's spot on. Okay, there were about 500 sheep on Tasmania in the year 1830. And if you had been using this model to predict the future, predict how much money you should invest in the mutton market and so forth, you could have made a lot of dough. If we continue on into the future, and we've just rescaled the graph so we've got some more space on both of the axes, the model predicts that in the year 1840, you should have about 2,500 sheep on the island of Tasmania. And our model has done really well so far. So, you'd expect that in the historical record, you'd see 2,500 sheep in Tasmania in 1840, but you don't. Instead, what you see in 1840 is about 1,000 sheep on the island of Tasmania. In 1850, according to the historical record, you see about 2,000. Okay, and here's where the difference between our model and the historical record becomes really stark. The model predicts something on the order of 6 times as many sheep, maybe more. It's up here in the range between 12 and 14,000, if I recall correctly. And this brings us to the point where our model is really useful, because clearly something is missing in this model. The predictions from the model do not match reality, and that tells us that we've left something very important out. It's quite possible that you've already realized what that is, because I keep talking about R max as being how rapidly an individual can crank out babies, or how it's the maximum per capita population growth rate, if there are no limitations on growth. The truth is, and this is exactly what happened in Tasmania, when a population starts growing, conditions rapidly start becoming much less than perfect. Okay, so you start running out of space for sheep. You might start running out of food or water for sheep. You could start running out of resources so badly that a lot of the individuals in the population might die. And at this point, of course, the births per individual minus the deaths per individual are not going to stay the same as they were in those first glory days when the sheep first arrived and there was plenty of pasture for everyone. The more individuals you get in a population, the more each individual suffers, and the more either their ability to survive is going to be reduced, or their ability to reproduce is going to be reduced. So R max is the per capita population growth rate that you would have observed in those first few years on Tasmania, because conditions really were ideal. But as the population grows, as any population grows, competition for resources makes conditions much less ideal. And so the growth rate that you see will not be R max anymore. This has been seen in an almost infinite number of circumstances out in nature. Sometimes what happens is that as a population gets more and more crowded, the survivorship will go down. It's harder and harder for individuals to survive. Sometimes individuals will survive perfectly well as the population grows, but they'll be able to have fewer and fewer offspring. Either way, the growth of the population slows down as it gets bigger. Okay, so clearly we need a model that can include this effect, the effect of competition. So we're going to put another mathematical term into our simple exponential model to try to account for this. Here's the term. The new term is here in the parentheses. It looks a little ugly, but we're going to go ahead and unpack it. And then we're going to look at how this model behaves differently than the exponential model that we've just been talking about. Okay, what we've just introduced is this term k minus n over k. And if you take this term all together or one variable. What that variable means is what fraction of the resources that exist in the environment are available to make the population bigger. Okay, so there's a certain amount of resources that are available on Tasmania for sheep. There's a certain amount of grass, water, space, and so forth. If you've got, let's say, 1,000 sheep on the island of Tasmania, they're going to need some fraction of those resources just to replace themselves. Okay, let's say they use maybe a quarter of those resources just replacing themselves. That means that 75% of the resources on Tasmania are available for population growth. They're available for making surplus offspring. Okay, and that's what this term is. It's what fraction of the resources out there are available for making surplus offspring. In other words, more than just replacing yourself during your lifespan. Some people have a difficult time understanding how this equation behaves and why. So I'm going to approach this in a couple different ways. Grab a hold of the way of explaining it that works best for you and ignore the rest. My only point of presenting it in different ways is in hopes that I'll be able to reach more students with at least one of these ways. What's important is not that you know more than one, but that you find the one that works for you and that you really grasp how these equations behave. Okay, the metaphor I'm going to use to explain how the logistic equation works is this. You've got an engine that runs at a particular speed and it's hauling cars of freight, cars of cargo, up a hill. R max, you can think of as how fast this engine can go, its maximum speed, when it is not hauling any cars. Let's say it's 100 miles an hour. Okay, N, the population size, you can think of as the number of cars that this train is hauling. Okay, so, and of course, the larger the population, or larger the number of cars, the more the train is going to slow down. K is this new number that we've introduced. And the name by which this number usually goes when you're talking about population growth is the carrying capacity. In this metaphor, the carrying capacity is the maximum weight that this train can move as it goes up the hill. When it is carrying K cars full of freight, it can't move at all anymore. So that's the point at which it stops being able to go up the hill. And this train is going to be moving at some speed. That speed is delta N over N delta T. Okay, it's not delta N over delta T, it's delta N over N times delta T, the per capita population growth rate. So, okay, remember the difference between the per capita population growth rate and the population growth rate. The per capita population growth rate is births minus deaths for the average individual in the population. You know, how many births am I likely, how many new offspring am I likely to have this year minus how likely is it that I'm going to die this year. Okay, so that's roughly like the speed at which the entire train is moving up the hill. And at first, this is what we're going to look at. Okay, we're going to look at the per capita population growth rate. Later on, in just a minute, we're going to look at the population growth rate, basically how many new individuals are being added to the population each year. But that requires an additional twist on this model. So I want you to get solid with what we're looking at now before we go on to that. Okay, so what I've said is that I want you to understand how this model behaves. And when we're getting at that is, you know, what does this look like when, say, N is large, when K is large, when R max is large? You know, as you change those variables, what happens to the speed of the train? And let's take a look at that. Okay, here's our equation. We've divided both sides by big N, so we've got delta N over N delta T over here. Over here we've got R max times K minus N over K. What does it look like when N is very small? In fact, the minimum possible size. It's very, very close to 0. Well, the rate at which this whole train is going to move up the hill is going to be really high. In fact, it's going to be very close to R max, because this is the minimum amount of weight that this train could possibly be hauling. It's going to be able to move very close to its maximum speed, the speed at which it would move if it weren't carrying any cargo at all. Okay, so when a population is very small, even in this new sort of slightly more complicated model that we're looking at, when a population is very small, growth is still essentially exponential growth. Each individual is cranking out a number of births per death that is very close to R max, the ability at which they'd be able to crank out babies if the world were absolutely perfect. Okay, when N is small, okay, each individual is not going to be able to crank out offspring at a rate equal to R max, but it's still going to be pretty high. The train is still moving pretty rapidly up the hill. In this case, you've got 3 train cars. The maximum it could possibly carry is 10. And so each individual here is cranking out 70% of the number of kiddos that they would be able to have in their lifetime under the most perfect imaginable circumstances. Okay, when N is half of K, well, then the speed at which the train is moving is half of the maximum which the train could move if it weren't carrying any freight. So, this should be pretty obvious, but as N goes up, the rate at which the train is going is much, much slower. It's slowed down to only 20% of its maximum rate in this case. And finally, you're going to hit a point where the number of train cars you've got is the maximum number of train cars that that train can carry. And at that point, there is no movement of the train. Okay, it's moving at 0% of its maximum speed. Basically, all the force which this engine is able to exert is able to keep the train from sliding back down the hill, but that's it. It's just stuck there. Okay, if you imagine that we added on another train car, so the N was actually larger than K, the train would begin to slide backward down the hill.